Yes, hello, thank you. So I'm going to talk today about polynomial invariants, both for classical programs and for probabilistic programs. And we're going to start very much in the first half with classical programs. So let's start with a very simple example. We have here a program and it takes two input integers, x and y, and then we initialize this variable set to 0. Then we have a loop, a while loop here, that executes a total number of y times because we initialize the counter I to y, and then in every iteration we decrease the counter by 1, right? So in every iteration we add x to z. So after termination, z is going to be equal to x times y. So this is an intuitive justification why the result of this program is the product of x and y. But of course, as you know, if you want to prove this formally, because this program contains a loop, what we need is a loop invariant. And the loop invariant we could use for this example here to prove that after termination z is going to be equal to x times y would be this invariant, that z is equal to x times y minus ix. So this is an invariant because intuitively in every iteration z is equal to x times y, but we're still missing I many x's. And also after this loop terminates, we also know that because of the loop guard, because we terminate that I is going to be equal to 0. So if we just substitute I is equal to 0 into the loop invariant, we immediately get the post condition. So given an invariant, or given this invariant here, the verification becomes very easy, or at least automatable. And also please note that although the program here is linear, it only uses linear or affine assignments, the invariant that we used is a polynomial. And now the question is, can we find such invariants automatically? But this is still an ill-posed question because in general there are infinitely many invariants, some of them more useful than others. But as I illustrated in the previous example, polynomial invariants are often quite useful. And so what we are focusing on is polynomial invariants, but not any polynomial invariant, but what we are looking for is the strongest polynomial invariant. So that is the set of all polynomials in program variables that are invariant for a given loop. Now you might say, okay, this is still an infinite set, but this is actually a very nice infinite set because it forms what is called an ideal. If you don't know what an ideal is, it's not so important. The important property is that every polynomial ideal has a finite basis. Quite similar to how a vector space is a collection of infinite points, but can still be described by just providing a finite basis. And for instance, for the previous example that I showed you, for the multiplication program, this single invariant that we had is actually already a basis, or a basis element of a basis with just a single element for all polynomial invariants of this loop. So the question, we now refine it, and the question now is, can we compute a basis for the strongest polynomial invariant automatically? And this is a question that has been studied quite extensively. So for deterministic, unguarded, and affine loops, that is loops as we've seen in the previous example, just a straight line loop body and no if statements, no non-determinism, and just affine assignments. For this class of loops, this problem is known to be computable. If you put in a single if statement, your program model immediately becomes Turing complete and the problem is undecidable or uncomputable. If we take out if statement again, but put in non-determinism, if we use affine arithmetic in the loop body, it's known to be computable. But if we use polynomial arithmetic and non-determinism, it is uncomputable. It's a very recent result. But there is a very important class of programs missing here, or very, you could say also fundamental, that is loops that are deterministic, or they don't use non-determinism, no if statements, but polynomial assignments in the loop body. And for this class of programs, computing the strongest polynomial invariant is also not known to be computable or uncomputable. And these are loops like this one, right? We have some initialization part, and then as I said, in the loop body, we just have no if statements, no non-determinism, but just some polynomial assignments. And you can also think of these loops as discrete time polynomial dynamical system, where the initial assignment part gives you the initial state and the system dynamics is given by these polynomials. And as I've said, for this class of programs, for this class of loops, computing a basis for the strongest polynomial invariant is not known to be computable or uncomputable. But there are also other problems, much more problems, whose status is unknown. For instance, just reachability. You're given a point and in the state space, and the question is, does this loop ever reach this target? So there are no algorithms known, but also no undecidability proofs. And the problems are believed to be very hard, and I'm going to show you that they are very hard. But there are no undecidability proofs, mainly because you cannot do a zero check in this program model. So many undecidability proofs reduce from some problem where you kind of have to encode some kind of zero check within your program model for which you want to show Turing completeness or undecidability. So maybe we have to reduce our expectations a bit, and maybe we cannot show undecidability, but can we in some sense show that an algorithm is basically impossible? And what I mean by this, I'm going to make this very precise. What we show in the paper is that both of these problems, or reachability for these polynomial loops and the invariant problem, is at least as hard as the Skolem problem. So what is the Skolem problem? The Skolem problem is about linear recurrent sequences. And you all know linear recurrent sequences. Just think of the Fibonacci numbers and the recurrence defining them. So a linear recurrent sequence, you're given a recurrence equation that is linear, that relates terms of a sequence together with initial values. And the question is, or the Skolem problem is, does a given linear recurrent sequence have a zero? And now also the status of this problem is unknown, whether it's decidable or undecidable. But this problem is actually as old as computer science itself, and it's connected. It has many connections to unsolved conjectures in number theory. So this is a problem where no one expects a PhD student to come up with an algorithm for it. And so what we prove in our paper is that both point-to-point reachability for polynomial loops and also computing a basis for the strongest polynomial invariant for polynomial loops, both of these problems are harder than the Skolem problem. And even more, they satisfy exactly this relation. So invariant problem is even harder than the reachability problem. I'm not going to show you the reductions we did from Skolem to reachability and from reachability to invariance, but let me just mention two short things about these reductions. So first, we reduced the Skolem problem to the reachability problem for polynomial loops. And we can also phrase the Skolem problem in a bit more computer science terms, because it's equivalent to the following. You're given a linear loop, so just the loop body is just a bunch of linear assignments, and you're also given a hyperplane in the state space. And now the question is, does this given linear loop ever reach this hyperplane? And when going from Skolem to polynomial loops, we increase the expressiveness that we allow in the loop body from linear to polynomial, but we simplify the target from a hyperplane to a point. But still, basically the expressive increase or the increase in the expressive power in the loop body takes over, and we show that reachability for polynomial loops is harder than the Skolem problem. And for the second reduction, we reduce reachability to computing the strongest polynomial invariant. And this basically means that polynomial loops are expressive enough to capture reachability within their invariance. And this is a fact that is not true for linear loops. So this was actually a very big part of our paper, the main part, but because this is a probabilistic session, let's also focus on this section here, and let's throw in some probabilities. Okay, now we have again a loop here, but now we also have probabilistic choice. In the loop body, for instance, x in every iteration either is increased by 2 with probability 1/2 or decreased by 1 also with probability 1/2. This is how this is to be read. And now for probabilistic loops, it's not so trivial what an invariant actually should be, right? Because in general, we cannot just write down a polynomial in program variables anymore, just because like the variables are now stochastic variables, right? They are different for different runs of this program in general. But what does not change over different runs of programs are the moments of variables. They are the same in every run of the program, the theoretical moments. So what we could do is we could write down some properties among the moments of program variables. For instance, that these are actually invariants, that the second moment of x, so the expected value of x squared, is actually equal to the expected value of y squared. And this is an invariant for this loop. And also so are the more complicated polynomials among the first moments and second moments of x and y. So we have here expected value of x, the second moment of y squared, and also mixed moments. These are actually all invariants of this loop. And even more, these four polynomials in the moments now actually again form a basis for all polynomial invariants among the first two moments of x and y, but only among the first two moments of x and y. And this is a notion that we formalized in our paper as well in moment invariant ideals. And if you are asking yourself in the previous example, why only the first two moments? Can't we now look for, let's say, all polynomial invariants among all moments, like among all infinitely many moments? But as you know, in general, you cannot pull out the power out of an expected value operator. And this is intuitively the reason why the set of all polynomial invariants among all moments does not form an ideal and in general does not have a finite basis that we could provide. But as illustrated in the previous example, if we consider all polynomials among a fixed set of moments, for instance, moments up to order of 2 or 3 or 4, then this actually does form an ideal again, and we can do something because it has a finite basis. But please note, it's a common misconception, we do bound the moments, but we do not restrict the degree of the polynomial. So this is still an infinite set. It's an infinite set of invariants among a fixed set of moments. And these moment invariant ideals then satisfy some nice properties. So as you would expect, if you increase the order of the moments that you allow in your polynomials, you get more and more information. And it's also a proper generalization of the invariant ideal from the beginning for classical programs. And for classical programs, the moment invariant ideal of order 1 already captures all the information. Precisely because if you don't have any probabilities in your program, this is actually true. You can pull out the power operator of the expected value operator. But for probabilistic programs, the subset relation, the first subset relation is strict, and you gain strictly more information the more moments you include. And because moment invariant ideals are a generalization of classical invariant ideals, we immediately inherit all the hardness results. Right? So if we have a single if statement in your loop body, you're uncomputable. But also this new hardness result that we showed for classical programs, if you have polynomial arithmetic and probabilistic choice, you are immediately Skolem-hard. What is not so trivial are computability results, right? For classical programs, the problem was computable if you only use linear arithmetic, but now we have also more constructs here. We have probabilistic choice. We may want to draw from distributions. So what can we do here? For instance, what about this loop here? We draw from Bernoulli distributions, from normal distributions. We have probabilistic choice. Also some form of if statements. And actually, for this kind of loops, we can compute the moment invariant ideals. And we have a tool and an algorithm, Polar, that can compute these things. And we can also characterize syntactically the loops for which this is possible. So, for instance, you might now expect why we can only support affine arithmetic and some form of polynomial arithmetic. We can support some if statements, but only over variables with finite support. For instance, here this if statements doesn't break computability because C1 and C2 are drawn from Bernoulli are only 0 or 1. Right? Then there are two other constraints. And if your program falls into this setting, Polar guarantees that it can compute any moment invariant ideal of any order. And maybe as a side note, this is actually where we started the investigations for these papers, also the hardness results at the beginning, because we had this tool and this algorithm already and this notion of moment invariant ideal, and also these restrictions here. And we were wondering, can we drop these restrictions or can we relax them? And for the last 3 points here, with a bit of effort, you can see that this is not possible to drop them, but the first one was puzzling us. And then we went down a whole rabbit hole and discovered that there is still some very much unsolved problems for classical programs that then would have implication on our work here, and that's how we ended up tackling these problems. So to conclude, for classical programs, invariants are necessary to automatically verify program properties. The strongest polynomial invariant is possible to compute or is known already to be computable for affine loops. But for polynomial loops and polynomial dynamical system, this problem was very much wide open, and also the reachability problem for these loops. And we showed that both of these problems are Skolem-hard and they satisfy actually this relation. For probabilistic loops, invariant ideals from the classical programs can very nicely be generalized to moment invariant ideals. And we also have a tool and an algorithm that compute it. Thank you.
Do we have questions? Yeah.
So for this reduction from Skolem to point-to-point to invariant generation, does this just say that if Skolem is undecidable, then so are the other two, or is it also making a complexity theoretic claim?
It's also complexity theoretic. Yeah.
So it's a polynomial time reduction?
Yes. Yeah.
Okay, so then whatever the complexity of the first is.
Yeah. Yes.
Thank you.
Thanks a lot for nice talk. It's just some naive questions. So your first example, even though it's a polynomial, it's multilinear. So suppose I focus on the multilinear invariant. Does that make things a lot easier?
In the invariant, I think it does. Yeah, I'm not. So everything becomes easier if you focus on the linear invariance. It's a very detailed observation. For those who don't know, because x and y are also just inputs, right? They don't change. So in this example, you might be able to use more simpler techniques because of this thing. But in general, for polynomial loops and polynomial invariants, yeah, we tackled this case. This is just by coincidence that this example is so simple. But good observation.
So you were talking about how for probabilistic programs, how the sequence of increasingly high order moments are strictly nested, and in some cases probability distributions are not even determined by the full set of moments if they grow too quickly. But in cases where they are, or maybe even where a finite number of moments determines the entire probability distribution, are there special cases with sort of this flavor in which you know that things are not as hard as possible, sort of depending on constraints on the moments?
What was the last part? Not as
well. So if you know that the moments are especially nicely behaved, or maybe determined by low order ones only, do you know that in those cases maybe you get positive results?
Yes, that might still be possible, and we investigated this part as well. Let me just go back to this slide. Where was it? Yes, here. This increasing chain, you mean? So we don't need the distributions to be determined by the moments. We just need the moment to exist. But yes, if you know some relationships among the higher moments, for instance, that the first two moments already specify the whole distribution, and you can basically automatically derive higher moments from the lower moments, then you could exploit these facts by adding this. Yeah.
So I think this is a pretty naive question, but in the polar, when you were talking about what polar can handle, in the case where you don't happen to use any randomness in your program, how do the guards here differ from the uncomputable deterministic guarded affine setting? What does finite support mean in that setting, and why can't I just compute a Boolean and put it as the guard to the if statement?
Excellent question. It's very much not a naive question. So the finite means that over the whole execution of this program, the variables that you use in the guard only take finitely many values. If you don't have any probabilities here, the only thing you could do is, for instance, set this to true, and then maybe in the if statement again to false, and you could do like a switch things. So
I see. And that's because there are no operations that create booleans other than the constants and the
yes,
Bernoulli.
yeah,
Okay.
exactly. Yeah. So the only thing you could do is like do case distinctions that run in a periodic fashion, basically, and then you could, in theory, also remove this again from the program by unrolling. Yeah.
Any other questions? Okay, I have a question. Since you go from affine to polynomial, one might naively expect that you can do the reduction with Diophantine equations. Can you give some intuition why that doesn't work?
Oh, I know that we tried that. Of course, it's a very first approach. We're going to polynomial. There must be some Diophantine equations. There are undecidable problems. Can't we use it? I don't remember now on top of my head why it didn't work, but we tried it and it was just impossible. Yeah.
Do you think you can give a reduction the other way to Skolem so that you have a ironclad argument for why you were not able to do the Diophantine reduction?
Yeah. No, I don't think so. Actually, this is a nice point. The problem could still be undecidable. This is basically just a justification that looking for an algorithm is probably not worthwhile your time. And actually, maybe if you let me, I mentioned this. So for moment invariant ideals, using probabilities, we have this Skolem-hardness result, but a very loose conjecture for me would be that it's still undecidable computing moment invariant ideals. And interestingly, there are undecidability proofs that rely on non-determinism, and if you replace them with uniform probabilistic choice, the proof still goes through. But for moment invariant ideals, there is one proof from last year that use non-determinism. If you replace it by probabilistic choice, it doesn't go through anymore. There is a discussion in the paper if you want some open problem to work on. Yeah.
Okay, let's thank the speaker again.